for the introduction. So the starting point of this presentation is on GaN devices, because now they are it's kind of technology which is widespreading in power applications, mainly due to some specific technological features that GaN devices have, like high breakdown field, good thermal conductivity, and so on. And they are very used mainly for DC power conversion, and from energy industry and even in automotive industry. The problem with GaN devices can be summarized mainly in limited durability, limited reliability. So they have problem with reliability, and there is also a very high variability of the parameters from device to device. So to have the widespread of those devices in the power application, it is required to put some monitoring system, control loops to cope with the problems, the challenges of GaN devices. So if we want to monitor them, and if we want to control, to make a system controlling and coping with those challenges, we need current sensors. So current sensor is a key element for GaN-based power devices. And what are the requirements on those current sensor? But mainly we need input range in the order of 10 amps or more. Accuracy could be 1%, in the order of 1%. Well, lower is better, but it's not the main problem. Another requirement is bandwidth. We need this, since GaN devices are used to switch at very high frequencies, as shown in the picture. So we need a wide bandwidth of the sensor, and most important is low insertion losses. Since current sensing is so fundamental, there are many solutions in the literature. The most used one is the shunt resistor. So place shunt in series to your device and monitor the current. The problem of shunt resistor is that they are lossy, so you waste power. Another typical solution from here, SenseFET. The second one from silicon-based power application is to use SenseFET. The idea is mirror your current that you have to monitor, scale down, and use this as a signal to check. The problem in GaN devices is that you have a very bad matching. So you don't know what is the scale factor. It's not so under control. So there is a research on doing that, but not so easy. So it's challenging. Other technique is monitoring the on resistance of your device. But I want to jump to the last one, which is use a magnetic sensor like a null effect sensor. What is the advantage of that solution? First of all, it is lossless. It fits very well the range, the input range required by the application, providing a good accuracy, good enough. And till now, they are already used in the application, but they are used, they are developed on different technologies, not the same technology of the GaN devices that you have to monitor. And in this presentation, we want to study what is it possible, and what would be the performance if we realize the Hall effect sensor in the same p-GaN technology used for the power device. We designed a couple of topologies, quite standard. We compared them, and we experimentally characterized the sensor in order to see what is the performance. So the technology is here summarized, how the sensor is realized. We started from GaN on silicon technology. Then on top of that, we deposit the p-GaN region all over the die. Then this p-GaN region is, well, actually it is used in the technology to remove the bidimensional electron gas. So in this way, the device is normally off. And then the p-GaN region is etched away apart in the gate region. So now you can realize your hand, your transistor. But in our sensor, we do not need the p-GaN. So we just removed all the p-GaN region on the top, and we realized the four contacts at the end. And the whole effect is realized on the bidimensional electron gas that we have between the GaN and the AlGaN layer. So, okay, what's very important is that no additional masks are used, so same technology used for the power device. What kind of devices have we implemented? Two most used topologies, which is the square sensor and the cross sensor. In both cases, they have the same size, so 35 microns by 35 microns. Can you see? No, just want to use a point. I want to use a point. Okay, okay, I will do it. So the branch in the cross sensor is 50 microns, so it's a little bit shorter, smaller than the entire device. Note that both the devices are fully symmetric. That means we can apply all the techniques usually realized for standard silicon-based sensor. And in this work, when we talk about the device and the test, so the single cell, it is not a single device, but a single single sensor is made by two devices connected in parallel, with one of the two 90-degree rotated with respect to the others, geometrically rotated. So, for instance, this contact A is connected to this contact A, B to B, and so on. This is the well-known pairing technique used to lower the offset. We made two different measurement setup. Oh, sorry, I just forgot that on top of our device on the test, we placed a metal strip like in this picture. So the edge of the metal strip is exactly at the middle of the sensor. And this has been done to resemble what will be the final application. The final application, we want to put the sensor close to the amp, and we want to measure the current flowing on the metal line that connect the drain or the source of the amp. So we try to resemble this final application. So we realized two different measurement setups. The first one, I named it on-chip test. In this case, we use a power supply in current limited mode to force the current on the metal trays. Obviously, this current is also monitored using a DMM. Then the current creates a magnetic field on that applies to our sensor. The sensor is biased using an SMU, so we force the current. It's biased at constant current, so we force the current and monitor the voltage, and then we measure the output voltage using another DMM. Since the output voltage is very low, we average over 10 readings for each current that we apply. The problem in this setup, it is, well, the advantage it is very close to the final application. The problem is that we do not know what is the magnetic field on the sensor, because at the end, the Hall effect sensor is a magnetic sensor. So we do not know what is the magnetic field. And the other problem is that the field is not uniform on that sensor. So we also developed the second setup. In this case, the power supply is used to drive an Alma coil. So we are not applying a current as input. We apply a field, a well-known magnetic field on the sensor, so we can better control and characterize our device. Okay, we made the static characteristics for both the device, square and cross, at 4 different bias current from 500 microns to 3 milliamps. And we did the characterization using the on-chip trace and the Alma coil. Obviously, what we measured and what we show here in these plots is the output voltage. So we have the Hall effect voltage plus the offset. If we look at the result from the Alma coil, we can see that the characteristics are quite linear. Linear enough. But if we apply the current on the metal strip, we can see that they are becoming there is a few percentage points of non-linearity effects. And that could be related to the Joule effect, because the metal trace is only 10, 20 micrometers far from the sensor. So we apply a current, this current heat up the device, and we have this thermal effect. From the static characteristics, we extracted the sensitivity. For all effects, they are usually characterized by looking at the absolute sensitivity. So the output voltage, the all voltage with respect to the magnetic field, and also the current related sensitivity, which is the normalized sensitivity, the sensitivity normalized with respect to the bias current. If we compare the two topologies, we can see that for all kinds of sensitivities, so absolute sensitivity, blue lines here, or current sensitivity, again, blue lines in this plot, the cross device is more sensitive than the square device. And this is what we expected, because it follows also the theory for silicon-based sensor. From those tests, we are also able to estimate what is the current to magnetic field transduction for our on-chip trace, and we estimated a transduction of 2.7 millitesla per ampere, which is current with the literature. And finally, we also estimated the offset, which is reported here as output referred offset, so the offset at the output, and input referred magnetic offset, so in Tesla. In that case, we can see that the square sensor, the square device, shows a lower offset. And again, this is in agreement with the theory of silicon-based Hall effect sensor. Finally, we also tested the input resistance. Okay, I have to accelerate. Because why the input resistance? Because it is important, because it affects how we can design the circuit that apply the bias current. Because if the resistance is very high, I need to realize a circuit with a very high voltage compliance. And also because this resistance will affect the power dissipated by the sensor. So if we look to the result, we can see that the input resistance does not depend on the magnetic field for both the devices, quite constant, but we have a kind of non-linearity effect when we apply the input through the on-chip trace. This confirms our idea that a Joule effect is happening. So to conclude, what we have shown is that we realized a null effect sensor in the same technology of the power device. It works, and we also made some analysis, some comparison between the two topologies that we proposed. What is, as a conclusion, is that, yeah, the cross sensor has higher sensitivity with respect to the square, and even though the square sensor show lower offset, well, actually, in both cases, the offset is too high for the application. We are talking about a few millitesla. So an offset reduction technique will be needed. In that case, from that standpoint, I would prefer to use the cross sensor and exploit the higher sensitivity. For sure, we need to better understand the Joule effect, and that must be accounted for in the final application. If we want to compare the sensor to standard silicon-based sensor, what we can say is that we have lower sensitivity, 100 volt over ampere Tesla with respect to 250 volt ampere Tesla, which is the usual standard number for silicon-based. But on the other end, we have a much lower input resistance. So that means we can apply higher current, higher bias current, and compensate for the lower current-related sensitivity. Future work, of course, we need to, this is just a preliminary result. We still need to characterize what is the dynamic performance of the sensor. We need to better characterize the temperature effect, which is very important. And finally, if we want to realize it in GaN device, in GaN technology, the challenge will be how to read out the very small output voltage. This is the next step. So thank you for your